Hi, Dave again. This is Lab 8. This week we're going to be looking at reliability growth data. We're not looking at everything that can be done with reliability growth data. We're going to look at a couple of simple models, one for discrete data, one for continuous data, and then we're going to talk a little bit about plotting it. So you see the objectives on the left-hand side. I will have this video posted. The Ryosoft updated their software with a new release about the 21st of August, so about a week ago. And they took down the videos for their old software and are currently producing videos for the new software. So there's not a video at the Ryosoft TV on this, but there is a manual available, and I put that on the shared directory. All right, let's start with discrete data. I want to start with a set of data that I came up with just to illustrate how this is done, where we've had batches of prototypes built and tested. So if you see on this spreadsheet, we had 10 items from a prototype, 10 copies of a prototype built, 2 of them worked, went back and did a redesign, 10 of them built and tested, 6 of them passed, another 10, 7 passed, and then 20, 20, 20 with 16, 17, 17 passing. So we've got groups with success failures established here. We're going to do this in Excel first because it illustrates what's going on, and then we'll quickly show how to do it in the Ryosoft package. But I'm a firm believer that you should be able to do these at least once in Excel so you understand exactly what's going on. It's very important to your understanding. All right, so let's make some calculations. If I had 2 out of 10 work, that means I had an estimated 20% success rate. So let's just copy that on down. So these are the estimated success rates for my various stages. And so I am seeing reliability growth, which is a good thing. Now I want to fit a Lloyd-Lipau model to this data using least squares. So that requires me to have 2 parameters, asymptotic reliability and then theta, where theta is the thing that's divided by the stage number that reduces it shows my growth parameter. Okay, so I'm going to pick some values to start with, the 1 and a 0.8 just to start with, and then I'm going to try and fit those. So my fitted data from this model, and this is why doing this by hand is important, is equal to this asymptotic value minus this growth parameter divided by the stage number. Okay, so we put that in and see it actually is 0.2, so a pretty good guess for me initially. And then as I copy that down, for these 2 particular numbers I guessed for the parameters, I'm getting values that agree or disagree pretty closely with what was actually observed. I can calculate what the errors are associated with that, the squared error, by taking the observed percentage minus the fitted, gosh darn it, the observed percentage minus the fitted value and square that. Okay, so that's a squared error term for how much my, oh gosh, should be squared to 2, having a tough time here today. So that's my squared error. It's not exactly 0 because some machine precision issues with Excel, but it's pretty close to 0. And similarly, I copy that down, and so I can see how far off my observed value is from my fitted value. Then I have something called my sum of squared errors, which is equal to the sum of those individual squared errors. So that's how it works. So my goal is I want this number to be as small as possible. So to do that, I go to the solver, tools, solver menu pops up, and I want to minimize that square, so I click the minimize button by changing these 2 particular cells, and I have a couple of constraints. My reliability has to be less than or equal to 1, and the second constraint is that this theta constant has to be less than or equal to whatever the reliability number is. And that's to prevent the predicted reliability from going outside the interval between 0 and 1. Okay, so with those done, I click the solve button, computer thinks about it for a while, and it gives me a couple of new estimates, which in turn are pretty close to what I actually had in the first place. And so that's my estimated asymptotic availability, and this is my theta, which is my growth curve. Okay, so we want to get a sense for how good this actually fits the data. So to do this, I'm going to plot my fitted values versus the observed values versus I. So here's my horizontal axis that I'm going to add one set of vertical data and a second set of vertical data. I'm going to go to charts, I'm going to go to scatter plot, and I'm going to put in the smooth line scatter. And so here I have, and I can see that my fitted model, which is in red, agrees really, really well with my actual observed reliability numbers. And so everything seems pretty good. And that's not really surprising because I made this data set up so things would fit well because it's a teaching data set. We will see later an example where things don't work as well. All right, so if I wanted to estimate what the reliability would be after the 10th stage, I could put in a stage labeled 10, and I'll just copy my fitted formula down to that, deleting here, and because remember that is a function of these fixed parameters and the stage number, and it says at the end of 10 stages of doing this, I would expect my reliability to go up to 91%, which is not a lot of gain for a lot of additional testing, but that's the nature of a hyperbolic curve. Okay, if I wanted to get confidence intervals for this, I could do it by hand, but trust me, it's really painful. So now that we have an understanding how this works, let's switch to the RGA software, bring it over, and look at this same data set in RGA. So here's the actual data set put in. The difference is they parameterize with the number of failures, not number of successes, but you can see that 20 minus 17 is in fact 3, so things are good. I select the Lloyd model. I select on least squares instead of maximum likelihood. The number of failures and the number of units are not cumulative, so I make sure non-cumulative is selected, and I hit my fit button, and I get numbers that are very close to what I got. I had 7909 here for alpha, they call it alpha, 0.7909 over here, 9896 here, 9896 there, they agree pretty well. And again, I can get a plot of this data, but there's a couple of things to note. The actual data positions aren't plotted here. These are the fitted data points plotted here in the black. That's going to be important later. But the good thing is I can get a confidence interval here. I get a confidence interval by adding confidence bounds on my plot. I want lower one side at 90% and click on it, and there I've got my confidence bound. So I not only have my estimate for the reliability, but I've got my lower confidence bound as a hedge against something going wrong with the model fitting. So that in turn is also pretty good, so I'm pretty happy with that. Another calculation I'm asked to do is that, let's say that the length of the mission that we did these testing on is not strictly a one-shot system. Let's say it's a 12-hour mission, we're counting successes and failures against this 12-hour mission. If we wanted to calculate the reliability, or the mean time between failure for that, based on that 12-hour time, we can go through and say, well, our reliability is equal to e to the minus t, or the mean time between failure. Solving for mean time between failure says it's equal to minus t divided by log r, where this t is my 12 hours, and the r that I'm using is the estimated reliability at the end of the 10th stage. So for example, at the end of my 10th stage, MTBF at the end of the 10th stage, I could say that that's equal to minus 12, which was the number of hours we said it was based on, divided by the log of this reliability, and I get this 128.04, which we have on the lab sheet. So that basically shows what's going on with the discrete data. Pretty quick, but time is short, and I'm assuming that you're pretty good by now at doing the Excel and pausing and play, so we can move this a little bit more quickly. Let's move on to continuous data. As you can see on the lab sheet, we're looking at some items that are put on test. What happens is the item is put on test until it fails, the time is recorded, an improvement is made, and either a new item or the same improved item is put on test again until the next failure. And so we have this series of 10 times representing times between failures. We want to fit a Dwayne model to this. To do that, we need to calculate the cumulative mean time between failures, which is the cumulative test time divided by the stage number. So for example, MTBFC for cumulative, for example, this is equal to total time of 18 divided by one failure, means our time between failures is 18. When we get to 80, we've had two failures. Our average time between failures is, oops, sorry, didn't quite hit this correctly. When we get to our second failure time, it's 40. Third, it's about 56, up to 60, 70, so on and so forth. So we can see that as we scroll this across, the mean time between failure, cumulative mean time between failure, is going up. So the Dwayne model says that the log of this mean time between failures is a linear function of the log of the cumulated test time. So to fit this model, first we have to construct the log of accumulated test time. I went too many T's here. Which is again pretty easy, equal the log of accumulated test time, and copy this over. And the log of the mean cumulative failure time, okay, which is equal to the log of here, and then we copy that over as well. Okay, so the idea is that this should be a linear function of the other. So that's easy to check. We can plot it. And we can also fit the least squares line. So let's actually go a little bit off the lab sheet. Let's just plot this first. Let's plot plot these two times versus each other and just see what we get. We go scatter plot and just take a marked scatter plot there. And that's not a perfect line, but it's roughly linear. Okay, so that's the argument that that's linear, and we can fit a line to it, and we can use that for prediction. That's the idea that we're coming to. All right, so how to fit a line? So to fit a line, we need a slope, and we need an intercept. Okay, and those slopes and these intercepts are going to come by, I'll just move this down a couple here, down to here. We're going to have a fitted value. Based on what that slope and intercept are, and that, so let's pick some values. Let's pick a half and 2 for right now, 0.5 and 2 just to get started. And so that says that if I take my intercept plus, actually intercept with locked values plus my slope times the log of t, that'll give me an estimate for what my fitted value should be. And it should probably be a 0.5 to get me in a better starting area. Okay, and then I copy these over, and then out of this I get a sum of squared error, just as we did before, which is equal to the fitted value minus the observed value, or minus the actual value squared. I got the squared right this time. We copy those over, and then we have a sum of these squared values. Equals the sum of all of this. And we want to pick the values of a slope and an intercept that make the sum of squared errors as small as possible. And again, that is a job for the solver, so we go to the tools, solver, minimize that cell, by changing the two values of the slope and intercept, and we solve that, and unless I've made some egregious typing error, we should get the same numbers again, 0.45 and 1.6. Okay, so then I've got my fitted versus my observed values. Now what I like to do is fit all of these, plot all of these together on this one scatter plot. I just use lines here. And so what I can see is that the red line are my fitted values, the blue is my actual values, and it's linear, and I've got pretty good agreement. So that's what I'm trying to show that. All right, so this mean cumulative time between failures is not the actual failure time, it's the average of the failure time. So by stage 10, it looks like we're lasting a little bit longer. There's almost 525 hours, 575 hour difference here, even though the cumulative average is only 170. So to get the instantaneous mean time between failure, estimated instantaneous, which says how I'm not how am I doing overall, but how am I doing at this particular point, that's equal to my predicted mean time between failure, which is e to the log of that, divided by 1 minus my slope term. Okay, which is in this case is 33, and I'm using slope and intercept instead of alpha and beta and otherwise, just so we don't get wrapped up in what the different terms are. And I can copy this over, and in particular, what did I do wrong here? Oh, so I did make this an absolute reference here. Okay, now when I copy it over, so it wasn't subtracting off. So now when I copy that over, I get the same numbers I have in the lab sheet. And so I see my predicted instantaneous mean time between failures now 264, which is the number we have in the lab sheet. If I wanted to calculate a future time, I would have to future total test time, say after 2,000 hours, I would have to say that that's going to be equal to the EXP of the log of 2,000 times my slope plus my intercept. Okay, and then divide that by 1 minus my slope again, which again is the formula that we have there. And we get a predicted value of 284, which again agrees with what I have here for my calculation, 284. So that's how we would do that, and if I wanted to get this 264, which I've done, is just the intermediate step for what the cumulative time is. But that's how we do that. Okay, so that's pretty good. This agrees with what I get in Reliasoft. If I go to my continuous sheet, I've actually entered the same data in. I've done the same sort of thing. I fit a model. This TMBF is my estimated instantaneous at the end of my test period, which is this 264 I calculated over here, which is also the 264 that I had there on that sheet. So those numbers agree. I've got a different parameterization, but the slope's about the same. This 4.533 agrees with what I have on my spreadsheet, so that's good. Two nice things: when I do the plot, I can also, I'm sorry, I missed this. When I do the plot of this, I can get the plot of both my instantaneous, which is the black line, and my cumulative mean time between failures. So I get both of that, and very nicely I can add confidence bounds. And this plot reports the actual data points, so I can assess the goodness of fit here, which I think is again not bad, same as I had before. This is a much better plot than I have with the Lloyd model. And to answer a specific question as to what my prediction is for end of 2000, I can put 2,000 times in here, add my one-sided lower confidence interval and calculate that, and again get the same number, but this time with a 90% lower confidence bound, which I like. So I'm pretty happy with that. I'm happy with the Reliasoft product. Quick mentioning, when I want to add these folios to RGA, right click on standard folio, and here I was adding a time to failure data with just the failure times, and those are my various choices to set things up. All right. Third thing I want to say is talking about plotting output. We saw the Excel plot for the fitted model, and we also saw the RGA plot. I believe I showed that, but let's go back and look at it again. Okay, and the point on this plot is it doesn't plot the actual data points. It plots the fitted points on the line with an interval that works back from it. So you don't get a sense for how good the fit is. Okay, so we're going to come back to that point. For the continuous data, both Excel and Reliasoft give you the actual data points so you can get a sense for the goodness of fit. Why this matters: there's a problem 15.8 in Blischke and Murthy, which has 20 data points. The data point looks like, where did I put this? 15.8, here we go. The data looks like this with 20 tests, each with 20 units on fails. See the number of failures observed. The important thing, in the last 10 tests, which is 200 units tested, there's a grand total of 4 failures. So 4 out of 200 looks like we're running at 98% reliability for my last 10 tests. But when I fit this to the model, because it's a hyperbolic model, and look at the plot, I don't get anywhere close to 98% for my estimated asymptotic or current reliability. It's underestimating it. And again, since the points aren't plotted, I don't see that. However, if I do this in Excel, same thing again, put the numbers in, all the stuff we did before, and plot the actual data versus the curve, you can see that the model is grossly underestimating the reliability that should be reported at this stage of time. And that's a real problem. Okay, so knowing that that happens in the software is something you have to know. It doesn't jump off the table at you, and that highlights this last point, that you have to know the strengths and limitations of your software tools, or you have to be prepared to do it yourself in Excel to check your work. And that's what I've tried to do in the course, is give you the skills to do it yourself, and then once you understand what's going on, work with the software. That concludes what I want to do in this lab. This should give you the skills to do with the homework. You will need plots like this to answer a couple of homework questions, but you know how to make them now, and you know the risks of using the Reliasoft plot naively. So I hope you've enjoyed this, and we will see you in class.